Cayley-Hamilton theorem. The theorem states every square matrix satisfies its own characteristic equation. The proof is as follows. We will try to prove the theorem for a third order square matrix, and it can be easily seen that the same way, in the same way, you can prove the theorem for square matrices of any order. Define square matrix A as A1, B1, C1, A2, B2, C2, A3, B3, C3. Then A minus lambda times the identity matrix can be written as A1 minus lambda, B1, C1, A2, B2 minus lambda, C2, A3, B3, C3 minus lambda. Then the determinant of the matrix A minus lambda I equals this determinant. As you can see, this determinant can be expressed as a polynomial of lambda, and the highest power of lambda that you can obtain in this determinant will be 3, and that is obtained through the principal element or the diagonal, the leading element, which is this, the product of these 3 elements. So we can write the determinant of A minus lambda I as a polynomial of lambda. So P0 plus P1 times lambda plus P2 lambda squared. Instead of writing P3 lambda cubed, since I know the coefficient of lambda cubed equals -1, I'm writing it as minus lambda cubed. I name this equation as equation 1. Then characteristic equation of the square matrix A is defined as the determinant of A minus lambda I equals 0. Since A minus lambda I, the determinant of the matrix A minus lambda I equals this polynomial, I am going to substitute the polynomial for the determinant of A minus lambda I. So P0 plus P1 lambda plus P2 lambda squared minus lambda cubed equals 0. Now, we'll define another matrix B as the adjoint matrix of A minus lambda I. Since A minus lambda I is the matrix shown here, you can see the adjoint of this matrix, all the elements of the adjoint of this matrix can be expressed as a polynomial on lambda, and the highest power, the polynomial, highest degree of the polynomial will be just 2. Because when we are considering the cofactor, for example, if we need the cofactor of the first element A1 minus lambda, it is the determinant B2 minus lambda C2, B3, and C3 minus lambda. It is a determinant of second order. So the cofactor will have a degree of 2 maximum. That means lambda squared will be the highest power of the cofactor. Therefore, adjoint of A minus lambda I can be splitted into the form Z0 plus Z1 lambda plus Z2 lambda squared, where these C's are square matrices of order 3. Okay. also name this equation as equation 2. Already we have another equation, so name this as equation 2. Okay. Now we have the property any square matrix M cross multiplied by its adjoint equals the determinant of the matrix M times the identity matrix. If we apply this property in this case for the matrix A minus lambda I, the adjoint of this matrix is simply B as we have defined above, equals the determinant of A minus lambda I times the identity matrix. A minus lambda I times, instead of B, from equation 2, I can put C0 plus C1 lambda plus C2 lambda squared equals, from equation 1, can be written as P0 plus P1 lambda plus P2 lambda squared minus lambda. Now both sides we have polynomials on lambda. Then we can equate the corresponding coefficients. If we equate the constant term both sides, we will get Az0 equals P0 times the identity matrix, which in this equation is equation 3. If we equate lambda to the power 1, we will get Az1 minus C0 equals P1 times the identity matrix, name this as equation 4. Also, you will get Az2 minus C1 equals P2 times the identity matrix, name this as equation 5. That is obtained by equating the coefficient of lambda squared both sides. Finally, if you equate the leading coefficient both sides, you will end up with minus C2 equals minus identity matrix. And this is equation 6. Now, if you multiply, if you pre-multiply equation 3 to 6 by identity matrix, matrix A squared, and matrix A cubed respectively, and if you add them all up, all the elements on the left-hand side will be cancelled, and on the right-hand side, you will get P0 I plus P1A plus P2A squared minus A cubed equals 0. Now, we know the characteristic equation is given by P0 plus P1 lambda plus P2 lambda squared minus lambda cubed equals 0. It is the characteristic equation. Now we see that this characteristic equation of A is itself satisfied by the square matrix. So it is the statement of Cayley-Hamilton theorem. Now there is an advantage by the application of this theorem. In this theorem, if we multiply throughout by the inverse of A, then we will get P0 times A inverse plus P1 A into A inverse becomes the identity matrix plus P2 times A minus A squared equals A inverse into the null matrix equals 0. Therefore, we can find a formula for the inverse matrix of A that is given by this equation. If it is a matrix of high order, if it is a fifth order or sixth order matrix, then it is impossible, it's nearly impossible to find the inverse manually by the ordinary method. Therefore, Cayley-Hamilton theorem will be more useful in those sort of applications. Thank you.